All right, we're now basically ready to describe the full RSA encryption protocol with all of its elements. You remember last time when we wanted to send a message to Professor Krepp, we had to ask him to run a key generation scheme. He had to generate public and private keys. This was the code that Professor Krepp ran. Let's just go and review that quickly now. First, we had to generate two random prime numbers. We didn't describe how to do that. We're going to do that in this lecture. Also, Professor Krepp had to generate this XBOM, which is basically just a random number, which is relatively prime to p-1 and q-1. You're going to understand soon why we did that. Also, we computed the multiplicative inverse modulo p-1 times q-1 of x spawn. Then Professor Krepp saves the public key and the private key. Professor Krepp can send the public key or can even just publish it on their website. Then there's an encryption and decryption protocol. But encryption is simply taking modular exponentiation of the message you want to send with XSpawn and PQ. And remember, XSpawn and PQ are part of the public key. And then the decryption protocol involves XSpawn inverse and PQ. And of course, XSpawn inverse is part of the private key. So this is basically what we use to create the RSA encryption protocol. We have to explain how to generate random primes. We have to explain why this encryption and decryption actually works. We also have to explain why this is likely to be a secure protocol, or mostly secure. Okay, so let's get started with that. The first thing we're going to do is to understand how to generate random prime numbers. So it turns out that to generate random prime numbers on the order of n bits, we can use Fermat's little theorem to help us out. It's actually incredibly useful. So first, let me explain one thing. If we pick a random number, any random number that's on the order of n bits, it has a probability of roughly 1 over n of being prime. So if you want to generate some random prime, what you can do is just pick any random number, check if it's prime, and if it's not prime, just try again. You may have to do this, let's say, about n times to find a prime number, but it will succeed eventually, and it won't take time. It takes on the order of n time for this algorithm to work and find a prime number. The only issue is, how do we check if a number is prime or not? That's actually a difficult question, but we have Fermat's little theorem to help us out. So notice that we proved in the last segment of the lecture that if we take some x, which is prime, and some base a from 1 to x minus 1, taking a to the x minus 1 is going to be congruent 1 mod x, right? That's a special fact for prime numbers, x. Now, it turns out that for almost all non-prime x, this is going to fail a lot of the time. What do I mean by that? I mean that if you pick a random base a from 1 to x minus 1, and you simply try to exponentiate it to the x minus 1, it will not be congruent to 1 mod x, with probability better than a half. So what do I mean by almost all non-prime? Well, it turns out that there are actually some exceptionally rare bad cases, and these are called Carmichael numbers. And they actually look like primes according to this test, even though they're not. So there's kind of two ways around this. One is these cases are so rare you can almost ignore them and simply use this test. This test is going to find a Carmichael number with incredibly low probability, and we don't have to worry about that too much. However, if you're interested in finding out a more sophisticated mathematical method around this issue, you can check the book. It actually describes a way to avoid these Carmichael numbers. But Fermat's little theorem does give us an almost foolproof way to check if numbers are prime. We can make this function Fermat prime test, which takes in an x and a number of times to do this randomized check. Okay, so for every iteration in the randomized check, what it does is it generates a random base from 2 to x minus 1. It does the Fermat check. It tests to see if Fermat's theorem it holds, which we know holds for primes and generally doesn't hold for non-primes. It takes the base a, raises to the power of x minus 1 modulo x, right? If the Fermat check is not equal to 1, it returns false. It keeps running this experiment, in this case 30 times, but you can decide how many times you want to do this check. And if it succeeds every one of these times on every iteration of this loop, then eventually it just returns true. This method checks if a number is prime and works with very high probability on almost all numbers except for the Carmichael numbers, which are the bad special cases. Okay, so now how do we actually generate random primes with roughly num bits if we want to have an n-bit prime number? It's very simple. We simply, in a loop, we're going to keep trying to find a prime number. What we do is we generate this random integer x, which just has num bits, many bits. Then we apply the Fermat prime test, and if it succeeds, we return x. Otherwise, we just keep trying, right? We just keep going through this loop. This is going to take roughly on the order of O of num bits to succeed. It may take a little longer because it actually is a randomized algorithm, but it should not take many, many more times than num bits. We're going to show later in the course that how to analyze these randomized algorithms, but this algorithm will succeed with very high probability in O of n steps. Okay, so we've seen this encryption scheme, but we haven't actually described why it works. What do I mean by why it works? Well, why is it the case when I use this encryption algorithm by just modular exponentiation and then do the decryption, which is again modular exponentiation, why is it that I get back the original message that I started with? That's a good question. So the first thing to note is that because of this line right here, because of E_inv is the multiplicative inverse mod p minus 1 times q minus 1, we can write that E times E_inv is congruent to 1 modulo p minus 1 times q minus 1. Recall that p minus 1 times q minus 1 is actually phi of p times q, right? And therefore, we can actually write that E times E_inv equals 1 plus some integer value times phi of pq. This is very important for some int k. So let's look at how we got this decrypted message. Decrypted is equal to, well, first you had to take the message m, raise it to the e mod pq, and then raise that to the E_inv, and then again take mod pq. Okay, so there's two steps. First you exponentiate it to the e, and then took that mod pq, and then again you exponentiate it to E_inv. That's what the receiver does, exponentiates to E_inv mod pq. Okay, we can actually simplify that. You don't have to apply the mod pq twice. It actually ends up being just once. It's sufficient. So this is actually m to the e all to the E_inv mod pq. Okay, given this expression, we can now, using our above formula, we can write this as being equal to m to the 1 plus k times phi of pq mod pq, right? Given this formula up here. Okay, now one thing we can make an assumption about is that the message m is relatively prime to p times q. It's hard to guarantee that, but it's easy to check on the sender side that that's going to be true, and can just make some modification if it's not relatively prime to pq. But almost all messages will be relatively prime to pq, so don't worry about that assumption. That's this assumption right here. Okay, so given that m is relatively prime to pq, we can actually write this as this is going to be equal to m, as m to the 1, times m to the phi of pq all to the power of k. I'm just rewriting this exponent as a product, and then a double exponent. This, of course, is mod pq. Now we're going to use Euler's theorem. This is the most important step. M to the phi of pq, because m is relatively prime to pq, m to the phi of pq is actually just equal to, congruent to 1 mod pq. So we can write this as, this is congruent to m times 1 to the k mod pq. But of course, 1 to the k mod pq is just 1. So the whole thing is simply congruent to m mod PQ. And you'll notice that we got back to the message M. And that's why RSA encryption actually works, and the decryption protocol undoes what the encryption protocol performs. The last remaining question I want to address is, why is it that this algorithm is secure? Now, I'm actually putting secure in quotes because we don't actually have a proof that it's secure in any real fundamental sense. What RSA relies on is some assumptions about what we think is possible to compute in a reasonable amount of time and what isn't. But this is actually still an active area of research, and we don't have a conclusive answer to whether there exists an algorithm that could break RSA. So the key detail you should know is that what RSA relies on is the fact that the receiver can maintain this private information, which is the primes P and Q. What the receiver publicizes in their public key is simply the product of P and Q. So it releases this object P times Q, but doesn't actually specify what P and Q are. It doesn't actually reveal the two primes that were multiplied together. Now notice that we actually have this very simple algorithm for decryption. If you know P and Q, right, the receiver, having received the message, can take the X-pawn, which was published as part of the public key, and the primes P and Q, and can just run the multiplicative inverse algorithm and the mod exp algorithm. Both of these take on the order of n cubed time, where n is the number of bits of these primes. So we have this efficient algorithm knowing P and Q, but let's say that you didn't know P and Q and you only knew P times Q. Let's just emphasize, why was it efficient? Why were we able to do this efficiently? Knowing P and Q allows you to compute this quantity P minus 1 times Q minus 1. Since we can compute P minus 1 times Q minus 1, we can compute the multiplicative inverse mod P minus 1 times Q minus 1 of this particular X-pawn. We can't do that if all we have is the product of P and Q. We'd actually have to factorize that P times Q into P and Q separately. Now, it's completely possible that there does exist some algorithm we simply haven't discovered yet that runs in a reasonable amount of time. It's sort of just believed that that's not going to be possible, or at least not with modern current technology. It is known, for example, that if we had a large enough quantum computer, that we could actually break RSA, and there is an algorithm known as Shor's algorithm which can do factorization. You see, one natural approach to solving this, you might just try to say P comma Q equals, let's say, factorize PQ, right? You could simply try to apply a factorization algorithm and then apply the original decryption protocol that we got here. Maybe just make output the result of this decrypt algorithm that knows both P and Q. That's fine. The problem here is that we believe quite strongly that there isn't a factorized algorithm, or at least not using modern techniques. Now, I will say that if you could come up with a method that could do factorization, or just solve this decrypt with PQ method that could just fill in the details here, you'd not only likely get a Nobel Prize, or at least some major scientific prize, but you'd also break the internet, because almost all of our standard transactions and interactions, for example, using SSL or HTTPS, all rely on the difficulty of being able to do this decryption without having the factors P and Q. So this is pretty cool, and there's still open questions here, and it's still an active area of research. You're going to learn about complexity theory towards the end of the course, and you'll be learning more about these types of quote-unquote difficult problems and what is solvable and what we believe is not solvable. So stay tuned for that.